So our next speaker is Carlo Buffardi. You are a PhD student at the University of Campania, and you're going to show us some interesting work from the area of Naples.
So, good morning, everyone. Today I will introduce you a part of my PhD thesis. The aim of this study is to find a relationship between the ground deformation and the geological and the geotechnical characteristics of the subsoil in a coastal and alluvial plain. The plain it's located in the south of Italy, near Naples, and it's the plain of the Volturno River. It's the largest plain in the south of Italy, and it's conditioned. It's always have conditioned by the volcanic activity near the plain. Just in the recent years, has been studied subsidence in this area. So the plain has a stratigraphic marker that it's the tuff that comes from the eruption of the Phlegraean fields of 39,000 years old, and that was incised during the lowering of the sea level after the last glacial maximum. After the incise of this surface, we get a valley that here we can see with the green border. Okay. And in some part, especially in the coastal part, this surface can reach 30 meters, the deep of 30 meters under this, the present sea level. The valley was filled after some retrogradation, aggradation, and progradation phases. And as we can see also in the present morphology, okay, here we can see the reconstruction that I just described to you today. And while in this figure that it's the DTM of the plane, we can actually see how the back dune zone has an elevation of 5 meters under the present sea level. So the starting point for the analysis are the subsidence rates that in the plane can reach also 38 millimeters per year. In this figure, we can see the rates that comes from the elaboration of the Envisat data. This is a cumulative chart of the average annual subsidence. We can also see how the subsidence it's actually happening, in the plane, and that the borders of the plane and the borders of the subsidence are actually overlapping. That means that the subsidence it's happening in the Holocene deposits that are on the top of the tough surface that I described before. After some preliminary analysis that help us to exclude any strictly relationship between the peak of the subsidence and the different land uses of the area, but also the groundwater extraction, we actually made a deep reconstruction of the Holocene architecture, where we reconstructed the depositional environment using also some radiocarbon dating. And after this phase, we did the analysis of the lithological and the geotechnical characteristics of the subsoil, and we made some confrontation with the different subsidence rates, the different subsidence rates that we found in the area. The dataset that we used was it's composed by more than 1,500 boreholes, CPT and CPTU. And from the boreholes, we did the analysis of the lithology of the area. We can see that we found obviously the tuff, that it's the it's the light brown the sand, that it's the yellow, and the clay silt, and also peat, that it's the more dark brown, and lots of peaty soils. We also obviously take in account the thicknesses of the different layers, and we put everything in a database, and we focused on the more compressible layers, so peat, clay, sorry, and silt. To better understand their role in the variability of the substance, we made a parameter. We made up with a parameter that we called the lithological ratio, that it's useful to understand the relationship between the thicknesses of the most compressible layers and the total thickness of the post-tuff deposits, so the Holocene deposits. We also made some classes to use them for the future analysis. We also take in account the wall thickness of the of the Holocene deposits, and also in this case we made some classes. We made all of these because just watching the subsidence and in stratigraphic architecture, we can find any pattern between these two elements. But putting together the thickness classes and the lithological ratio and plotting them on the subsidence chart, we can actually see that there is a relationship. In fact, in correspondence of the strong substance, we found high thicknesses of clay and peat, but low thicknesses of the wall Holocenic deposits. While in the middle, where there is the middle substance, there is high thicknesses of peat and clay, but also high thicknesses of the Holocene deposits. So the medium substance is correlated with the large thicknesses of compressible layer, but oddly, the strong substance correspond to a small thicknesses of Holocene deposits. So this led us to think that the main role in the variability of the substance is played by the younger deposit and their primary and secondary consolidation. Okay, after that, we made the analysis of the geotechnical data. We made some CPTU near the coastal area. And here we can see the subsidence transect and here the reconstruction of the lithology. We analyzed them, and we analyzed some of the main parameters of these of the CPTU. So we analyzed the core resistance, but also the friction ratio. The most interesting consideration comes from the soil, the analysis of the soil behavior type index that put together the previous two parameters, and that it's useful to understand the soil's behavior type based on the geotechnical characteristics of the soil. So this parameter tells us that even if we have layers that lithologically are the same, they have different geotechnical behavior. We can also see this here, where we can focus on just these two CPTU. We can see that they are almost the same with a lot of peaty soils. Actually, in the number 5, we can also find some sand, but oddly, the peak of the subsidence, it's up, it's here. Yes, in the 5. To explain this, we just plot the soil behavior type index on the SBTN plot, and we can actually see how the number 5, it's made up by a major number of layers that behave like clay or silty clay than the number 4, where there is no peak. So how we can explain this kind of behavior? We are talking about soils that have the same lithology, but they are, under a geotechnical point of view, very different. We can explain this putting into the analysis also the depositional environment. So we can see that, obviously, after some analysis, that the number 5, in the number 5, we can find layers that can be associated to a swamp, while in the number 4, we can find layers that can be associated to a floodplain or a lagoon. This is actually a preliminary phases of this kind of analysis, but we made other analysis like that in the area, and actually we find let's say that we can trust them, and we can say that it makes sense, this kind of thinking. Okay, so just to conclude, we can say that the composition of the Holocene sequences affect the subsidence rates, and that the thickness of the most younger layers it's highly linked to the variability of the subsidence. And one of the most important things is that a combined approach that mix up together the geology and geotechnics can actually highlight how the same lithology that belong to a different depositional environment can have a different degree of consolidation. For the future, we understand the importance to reconstruct the formation of the plane, so we will implement it to simulate the natural consolidation through the use of the NatSub 3D models. Thanks.
So well in time, Carla. Nice.
Thank you.
So we have time for several questions. Are there questions from the audience? Gilles?
Yes, thank you very much for your interesting talk. You said that primary and secondary compression is one of the factors that cause the land subsidence here.
Yeah.
There's also peat quite shallow in the stratigraphy. So do you think that peat decomposition, as we heard in the previous talk by Erne, could also play a role in land subsidence?
Thank you for your question. It's not easy to give a certain answer, also because we didn't make any analysis of that kind. So I can't say an answer with certain, let's say. I can say no or yes. We didn't know it yet. Maybe yes. Yes.
Are there other questions?
Thank you for your presentation. Just one fast question. Did you measure the pre-consolidation stress?
No. No, we didn't do it. No.
Maybe you can derive that from the CPTs, right?
Yes, maybe we will be the next step. Let's say we will use them in the most complete way. Let's say. Yes.
Yeah. Are there questions? Yeah.
Thank you very much. I'm curious about what of the point that you use in the CPT values to compare with the subsidence. As we know that the CPT is to assess the shear stress abilities of the soil. And I'm thinking that the consolidations will be more like the normal stress inferences. So maybe I do not catch up the point. And I'm curious why you would like to use in the shear behaviors to compare with the consolidation.
I don't think that I get the question. I'm sorry.
Okay. Yeah. CPT
Yeah.
commonly is for the shear abilities, right? Yeah, but the consolidation is like the normal, like the loadings or like the effective stress. There are many occurred from the how to say it's the normal stress concept or the effective stress concept. So I'm curious why you would like to compare these two for the mechanisms.
But you basically want to know why you use CPTs for this kind of compression analysis, so to say, because he says CPTs measures more like shear strength instead of it's not blunt compaction. Yeah.
So the main reason that we are using the CPT, it's the availability of the data, but also because it's the cheapest trial that we can do on the plane right now. That's it.
Yeah, we have time for because you were. We have time for a few questions. I have some questions, by the way. So I was triggered by two things. First of all, you said the younger layers are more compaction prone. Is it due to the depositional environment, or
Yes.
they experience less loading? So what's the difference with the older layers? I mean, I thought they were all let's say flood basin deposits.
No, because the story of the plane, it's not so simple. So there were different phases, and so there are a lot of different depositional environment.
Okay, and then the younger maybe contains less silt or something like that.
I'm sorry?
And the younger clay contains perhaps less silt, so
Yes.
it's more compressible,
Yeah,
something like that.
also more, they are so more peaty. They are more peaty than the other
Oh.
one.
Ah, okay. And my second question was actually when you compared CPTU 4 and 5,
Mm-hmm.
you had some sort of lithological column made
Yeah.
out of it, and then it almost showed that from bottom to top in CPT 4, I think it was marsh. So that means that throughout the entire Holocene, the accommodation space was filled in with marsh deposits.
Here.
So the swamp deposits. So what kind of how does that work in such a confined basin? Because I would think, you know, you have like river avulsions all the time and plastic splays embedded in your swamps. See this one, this is
Yeah.
the green one.
Okay.
Yeah. So throughout the entire Holocene, it was a swamp. That's basically what you
Yes,
were saying.
it's everything as swamp, just from the analysis of the burrows.
Ah, okay.
Yeah.
Okay. Well, let's see. Henk, or you have a question? Let me see. We have 2 minutes. 2 minutes, Henk. Yes.
Yes, a quick question.
Okay.
I missed the first part, so you may have told this, and I heard a primary and a secondary compaction as causes of subsidence. For primary compaction, you need an effective stress increase at
Yes.
some moment in time. That's the driver, let's say, of subsidence. Could you explain what you think is then the driver?
For the primary consolidation, I think that the primary, it's just especially for the lowest layer of the plane, it's just the compaction and the layering of the other soils. Yeah, it's just the sedimentation. We think that it's the most natural thing to say, to think.
Okay, thanks, Carla.